Welcome to Mr. Haven's Physics Power Hour, or at least the next few minutes anyway. This PowerPoint is going to be about Newton's laws of motion. We've kind of already talked about them. We just need to get it down on paper so we know what they are. So the first law for Newton's law is the law of inertia. We'll talk about that. The second law is summed up in force equals mass times acceleration. And the third law is the action-reaction force pairs, and we'll talk about that as well. So, while most people know what Newton's laws say, many people do not know what they mean, or sometimes they just don't believe what they mean. So the first law of motion, the law of inertia. An object at rest will stay at rest, and an object in motion will stay in motion at constant velocity unless acted upon by an unbalanced force. So we've kind of drawn free body diagrams and talked about this, so we'll continue with that as well. The law of inertia. Inertia is the tendency of an object to resist changes in its velocity, whether in motion or motionless. So if it's at rest, it wants to stay there. If it's moving, it wants to stay moving. And we'll talk about why things sometimes do not stay moving. So you see the golf ball here. Unless acted upon by an unbalanced force, i.e. the golf club, that golf ball would sit on the tee for forever. Except in West Texas where the wind would probably blow it off. But in this case, it would want to stay there for forever. So why then do we observe everyday objects in motion slowing down and becoming motionless seemingly without any outside force? And the answer to that is friction. Friction is what slows things down because surfaces are always in contact with each other, and when they're in contact there's friction between them. And so friction slows things down. So here we go. That unbalanced force is friction, as we said. And there are four main types of friction that we talk about. Sliding friction is like ice skating. Rolling friction is like bowling. Fluid friction, that's air or water resistance. We'll talk about that a little bit. And then static friction, that's the initial friction when moving an object. So before you move a desk, initially it is not moving. The force it takes to get that desk moving is overcoming that static friction. So in class I slid the book across the table to demonstrate it, and it slid to a rest position. The reason it came to a rest is because friction. So when I took the book and I pushed it, eventually it stopped. If it were not for friction, it would continue on until it fell off of the table. And so it says in this slide, in the absence of friction, it would continue the same speed and direction forever. So that's the way it works. No friction, keeps on going. So here we go. We got our guy driving on Saturday night, runs into the brick wall, clears it, just barely. He almost nailed it, but he didn't. So because of inertia, an object resists its change in motion. When the car is going 80 kilometers per hour, so is the man. So when he hits the brick wall, even though the car stops, he continues on at 80 kilometers per hour. That's why we have seat belts and things like that and airbags, because of our inertia. Newton's second law, force equals mass times acceleration. So the net force of an object is equal to the product of its mass and acceleration, or simply the equation we've already learned, force equals mass times acceleration. So when mass is in kilograms and acceleration is in meters per second squared, the units of forces that we have already learned is in newtons. So our unit of force is newtons, and 1 newton is equal to the force required to accelerate 1 kilogram of mass at 1 meter per second squared. The second law continued. So here's an example. How much force is needed to accelerate a 1,400 kilogram car 2 meters per second squared? So we write down the givens. Our mass is 1,400 kilograms. Our acceleration is 2 meters per second squared. Our unknown, what we want to know is what is the force. So we write down our equation. Force equals mass times acceleration. Then we solve or substitute. So we plug in our numbers. Force is equal to 1,400 kilograms times 2 meters per second squared. And then we solve. So you plug that in your calculator and you get 2,800 kilogram meters per second squared, or 2,800 newtons. And that's how you solve this equation. This chart really shows a whole bunch of stuff. I don't really care to write anything down on this chart. We'll talk about it when we get to class. But the part at the bottom is what's most important. So if our mass remains constant, doubling the acceleration doubles the force. And if the force remains constant, doubling the mass halves the acceleration. So it depends on what side of the equal sign we're talking about. If the force on the left is constant, then what happens to either mass or acceleration? The opposite happens to the other one. So if mass goes up, acceleration goes down. If acceleration goes down, mass goes up. And we've kind of already talked about this a little bit, and we'll talk about it more in class. So here's a little check your understanding kind of thing. There's 4 problems. I want you to, pause it here, read them, and work them out. Number 1, what acceleration will result when a 12 Newton net force is applied to a 3 kilogram object and then a 6 kilogram object? Number 2, a net force of 16 newtons causes the mass to accelerate at a rate of 5 meters per second squared. Determine the mass. Number 3, how much force is needed to accelerate a 66 kilogram skier 1 meter per second squared? And then number 4, what is the force on a 1,000 kilogram elevator that is free falling at 9.8 meters per second squared? So you should pause now, work these out, and then on the next screen there'll be the slide with all the answers. So the answers to our problems: the first one, the 3 kilogram object, its acceleration is 4 meters per second squared. The 6 kilogram object, 2 meters per second squared. So you see there that we doubled the mass and we have the acceleration. Number 2, the mass is equal to 3.2 kilograms. Number 3, 66 newtons. And number 4, 9,800 newtons. And if you have questions about any of these, we will talk about them in class. So this brings us to our third and final law. For every action, there's an equal and opposite reaction. So you got this person here, they're sitting down in the chair. So the person, which we'll consider object A, interacts with the chair object B. The person exerts a force downward on the chair, and the chair exerts an equal and opposite force on the person. Otherwise, either one or two things will happen. The person would fall through the chair, or the chair would push the person out. So the body exerts a downward force, the chair exerts an upward force. So the two forces are called action-reaction pairs. So the action is the person exerts a force on the chair. The reaction is the chair exerts a force on your body. So action-reaction force pairs. Just like in this one, the baseball bat, the ball comes in and forces the bat to the left. That bat forces the ball back to the right. So the action is the ball forces the bat to the left. Reaction, the bat forces the ball to the right. And that pretty much covers Newton's laws for today. Y'all have a good evening.